warahmatullahi wabarakatuh. Today, we will continue our chapter 3 on basic equation in fluid mechanics. So, we look at, at this part, we insert all the momentum. Okay, after we learn the Bernoulli equations and continuity equations, so we learn now and the momentum. Okay, so momentum can define as mv, where m is a mass and v is velocity. Momentum is equal to m times by v, mass times by velocity. So momentum equation expressed from second Newton law. Okay, the fluid contained in the tube AB here. Okay, A, B, C, D will moving to A, B, D, C, D after time changing in dt. Okay, so momentum A, B, B, D, D, B, B, okay, B, 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 B is equal to mass times by velocity, so we get this one. Okay, momentum changing in times, we get the density at density 2 times by area of 2 V2 squared over dt, changing in times, so we get. So no need to worry, just use this, all this equation will be given, so don't worry. Okay, momentum rate. Okay, this is for the momentum. So in steady flow, we use the continuity equations in momentum rate. So we get the force. Okay, force, the equation of force. Okay, so and this is the equations for momentum. Okay. Okay, so application of momentum equations, we can look at the structure open to the atmosphere. So force of pressure, conduits and bend, force of a stationary vane or blade, and force of nozzle. So these four types of structure, we can know to apply the momentum equation at this side. We look at the example here. Okay, the water passage in figure, this one, figure below, is 3 meter wide, normal to the plane of the figure. Okay, so the wide normal here. Okay, so this is 3 meter here. Okay, wide normal is 3 meter. Okay, so determine the horizontal force acting on the shaded structure. Okay, this is the shaded structure. Okay, this is the structure. Okay, assume ideal flow. So we look at the free body diagram using the continuity equation. Okay, from this diagram, so we do the free body diagram using the force and the force resistance for the free body diagram, that so that insert to this structure. Okay, so at the free body diagram, so there is a F1 here. Okay, but before the structure, F1 here, and F2 here after the structure. Okay, Fx, this is a horizontal force. Okay, using to the structure here. So using the energy equation, or the Bernoulli equation, so we find that pressure at structure 1 to the pressure at, okay, this is at 1, okay, before the structure, and point 2 is after the structure. So that's why we get the F1 and also the F2 here. So we get the energy equation at point 1 here and at point 2 here. So we get pressure at 1 and pressure at 2 is 0 because this is atmosphere. Okay, so open to the atmosphere, so that's why we get the pressure at 1 and pressure at 2 is 0. Okay, so after we use the energy equation, so we get this one. Okay, this is 0, this is 0. So just only have the Z1 is 2 meter, so that's 2 meter. So just only have V1 squared over 2G is equal to Z2 is 1 meter, so we use this one. Okay, so we get this value for the energy equations. So after this, you use the continuity equations. We use this one and you get this one. Okay, after you just get the V1 in terms of V squared, so you just put this value to this equation. So until you get the V1 2.56 meter per second, V2 is 5.11 meter per second. So we get the Q is equal to A1 times by V1 is equal to A2 times by V2 because we use the continuity equation. So the same value of the Q. Okay. Okay, after you use the Bernoulli equation and the continuity equation, so you must apply the momentum equation to the free body diagram. Okay, so F1 minus by F2 minus by Fx. So the equation is, for momentum equations, is density times by Q times by V2 over minus by V2. Okay, you just insert all the value to these equations until you get the force of X axis. Okay, X is horizontal. Okay, you get the force of horizontal at the structure. So we get the 4.91 kilonewton. So the error of the force is this one. So okay, so your free body diagram that you sketch before is the right sketch because you get the error like this one. Okay. We finish for the example 15. So we look at the example 16. Okay, using flow occurs over the spillway of constant section is shown in figure below. So the given that Y1, Y2 and determine the horizontal force on spillway to find the horizontal force. Okay, horizontal force. Okay, X is horizontal. Okay, on the spillway per meter of spillway width perpendicular to the spillway section. Okay, first you must know that energy equation, Bernoulli equation, energy equation or Bernoulli equations. And second, you must know the continuity equation. Okay. And find the value of the V1 and V2 and the Q. Okay. After you get this value, you must apply the momentum equation to the free body diagram. Okay, so the free body diagram here. So F1 here, okay, F2 here, and the Fx here. So Fx is the force that apply to the structure, the spillway. So F1 is the force that come from the water at depth 1. And F2 is the force that comes from the water at Y2. Okay, so you apply the momentum equation to the free body diagram. So we get the F1 minus by F2 minus by Fx. And times by is equal to times by density times by Q times by V2 minus by V1. Okay, so just put all the value in these equations. So we get the value. Okay, water Fx X on the spillway to the right with this. Okay. Okay, so force of pressure, conduits and bend. So this is on conduits and bend. Is consider the case of horizontal flow to the right through the reducer. A free body diagram of the forces acting on the fluid mass contained in the reducer, the control volume. So we shall apply Fx, okay, to this fluid mass to examine the forces that are acting in the x direction. Okay, this is for the conduits and bend. Fx is on forces that are acting in x direction, is horizontal. Okay, so we have the PA times by A1, P2 times by A2 represent pressure force that fluid located just upstream and the just downstream. Okay, the force Fx represent the force exerted by the reducer on the fluid. Okay, the fluid here. So neglecting shear force at the boundary of the reducer, the force Fx is resultant effects of the normal pressure force that the wall of the reducer exerts on the fluid. Okay, so this is the equations that apply for the bend and conduits. Okay, so this is on x direction. Okay, but for the reducing pipe bend, so if the fluid undergoes a change in both direction and velocity, as in the reducing pipe bend, the change in fluid momentum in the x direction give, okay, because they have the bend here, so you must consider the angle here, okay, the angle here, because this is in bend. So you must consider x direction and also y direction. Okay, but this is for the x direction, so you must consider the cos theta. Okay. Okay, in this the y direction. Okay, so in this y direction, so you must include the vertical direction here. So you must use the sign. Okay. So this is the momentum equation applied for the y direction. Okay, so just remember that only the conduits and the bend, they have the two direction, y direction and x directions in momentum. Okay, so look at the example 17. So a water flows in a pipe which bends to the horizontal axis at 55 degrees. So the inlet pipe's diameter is 600 mm and reduced to 300 mm at the end. Okay, from 600 mm to 300 mm at the end. So given the inlet pressure, so inlet pressure here P1 and flow rate, okay, respectively, neglecting the friction, calculate the resultant force at the bend. Okay, to find the resultant force at the bend. Okay, this is the angle here for the bend. So the flow is from this inlet to the outlet here. Okay, the flow is from inlet to this one flow. Okay, so we know that V1 is equal to Q over A1. So we know that V1 is 1.6, 1.5 meter per second for this at this point. So using the energy equation or Bernoulli equations, okay, this you must find the V1 and also the V2 because they give you the diameter and the area. Okay, so you can find the V1 and the V2. After this, you find the energy equation. Okay, using the energy equation from the point 1 to the point 2 here. So just put all the value inside these energy equations. So you get the P2 123 kilopascal. Okay, after this, you apply for the momentum change in x direction and momentum change in y direction. Okay, so apply the momentum change in x direction. They have P1 times by A1 minus by P2 times by A2 cos theta minus by Fx. So the density times by Q times by V squared times by cos theta minus by V2. V2 cos theta minus by V1. Okay. So just remember that for the x direction, you must the cos theta. Okay. In the y direction, you must use the sin theta here. Okay. So we get this Fy. They have no vertical axis for the Fy, so they just don't have the P1 here. Okay, so they just P2 only sin theta. So just insert all the value here, so you get the Fy 7970 newtons, and the Fx is 1 using the arrow here. So after you get this momentum in y direction and x direction, so you must find the resultant force. Okay, so resultant force is Fr is equal to power of Fx squared over Fy plus Fy squared. Okay, square root here. So we get the resultant force 33 kilonewton. Okay. Okay, so the direction of resultant force. Okay, the direction of resultant force, we get the tangent theta is Fy over Fx. So we get the direction of resultant force here. Okay, therefore the resultant force F is 33 kilonewton x angle and from horizon. Okay, so look at also the horizontal plane. Okay, calculate the magnitude. So the magnitude, okay, and the direction of the resultant force on the stationary blade. Okay, so they have the angle here and flow here. So you first you must find the Q, A, flow rate at A. So find the flow rate at QB. Okay, after this, you use the momentum change in x direction. Okay, and x direction, you must use the cos. So you get the Fx is 2.12 kilonewton. Okay, so you use the momentum changes in y direction. So we get the Fy is this value, and you use to find the resultant force and the direction resultant force. So we get this value. Okay, and this is the same also to find. Just remember that conduit and bend, you must find the Fx direction in x direction and Fy in y direction. Okay, assume the friction is negligible. So find the component of the force acting on the vent and the force component normal to the jet and the magnitude. Okay, this is the solution to find the, okay, to bend at this the bend. So they have the Fx direction and Fy directions. So we get the value here, and you must find the resultant force and the direction of resultant force. Okay, therefore the resultant force and x in this one, so we get the value here. Okay, example, this one is also the same. Okay, you must find the x direction and y direction and find the resultant force here. Okay, so this moving van. Okay, resultant force at van is the van moving at velocity in that direction, also in the B. So you use this one. Okay, so and also this. Okay, and also, okay, that's all until this one. So just remember that for the momentum, so you must use the continuity equation, you must do the Bernoulli equation and also the momentum equations. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.